Part B, with reference to the data below, explain how fission and fusion processes differ in their release of energy. And we're given some binding energies per nucleon: deuterium, helium, iron, and uranium. So I think a really good graph to sketch would be nucleon number and binding energy per nucleon. Which goes something like that. Very good graph to remember. You know, it's an answer. I know the paper gives you lines to write on, but I think the graph is going to speak very well. And so hydrogen's right at the end of this, obviously. We've got iron up about here, uranium there. Helium has a, you know, this is sort of a bit spiky at low end. Helium sits up with a really, really high binding energy per nucleon. Not given hydrogen, we're given deuterium. Okay, fission and fusion processes. Well, in fusion we have two small nuclei, or more than two, combine to give one larger one. And the point in fusion is that you're moving this way up. And the larger one has more binding energy than its constituents. So these things are bound more tightly. It's given off energy, more binding energy than constituents. Energy is therefore released when this happens. Because these are held more tightly. It's like two objects coming together under gravity. You come together, they got less potential energy. When they're close together, that energy's being released. That's where it comes from. You're moving that way. Your fission, on the other hand, goes that way. So fission to one large nucleus goes to two or more small ones. This collection has more binding energy again than that one. So again, energy released. So that's fission. Fusion, fission. The question says with reference to the data below, so we'd better do some references. So example of fusion might be deuterium, two of them goes to a helium. I think, I'm not a nuclear physicist, but I think that process is a bit more involved than that, than just sticking them like that, but there we go. Binding energy before. So that's just Now we have to think about this, but the data's binding energy per nucleon. Deuterium has 2 nucleons, so it's 2 times 1.12 mega electron volts plus another lot of 2 times 1.12 mega electron volts, so that's 4 times 1.12, which is 4.48 mega electron volts. I don't see any reason to turn that into joules. Mega electron volt is a measure of energy, just like a joule is. Binding energy afterwards. So it's 4 nucleons in the He times the helium-1, which is 7.08 MeV, which is going to be 28.32 MeV. So we've got much bigger. So it implies lots of energy released. Do the same with the fission. I'm going all over the place with this writing, but U goes to, now you split the uranium-238, you get all sorts of things. So one might, not so obvious to do this calculation, but what we can see anyway, you might get an ion plus other things, a few ions anyway. But the point is, per nucleon, you've got 8.79, and here you've got 7.57 MeV, so you've got a binding energy increase. Note, of course, the number of nucleons on both sides is going to be the same, whatever it turns out. So we had 4 here, 2 lots of 2, and 4 over here. Nuclear fission and fusion.